Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everybody. Today I am going to talk about software warning mechanism for device pass-through and sharing. This is the joint work with Saurabh himself. So current network processing techniques has higher overhead, particularly for the virtual machines, and the network processing in the guest requires special devices like SR-IOV device. And still with the SR-IOV device, there are some limitations such that the in-guest communication is not very high performant. We trying to solve this performance with only software only mechanism, so we don't need any special devices, and using our technique, guests can directly talk to each other. We provide in-guest switching, and we are also secure against any malicious guest. In the rest of my talk, I want to explain what this SR-IOV device is and how we are doing these things. So often we run several applications on our machine. All these applications share the same system resources. For example, all these applications share the same network device, but since these applications are untrusted, we run them in lower privilege mode, and we put a piece of software in higher privilege mode which directly talks to the device and share this device to these applications. So when we run a simple socket UDP benchmark on a 10 Gbps network card, we found that it is very slow. So we achieve around 1/31 to 1/33x of maximum achievable throughput with 60 bytes of packets, and with 1500 bytes of packets we get around 1/4 to 1/5x slowdown. The reason why 60 byte packets performs very bad as compared to 1500 byte packets, let's understand how device driver work. So device has a circular queue which has 512 slots, and when we send these packets, we put these packets inside the queue. Notice the CPU overhead is per packet, whereas the device throughput is measured in terms of bytes. Hence, the smaller packets stresses the CPU more than the larger packets. Here is a work which profiles the network stack and found there are several pieces which are responsible for this throughput degradation. And they come up with a bunch of optimizations, but the main optimizations were that they create a user ring which is similar to the hardware ring, and they share this ring with the kernel in some producer-consumer manner. So this is the Netmap user ring, which is initially filled.
That's a question.
Oh, yeah.
So I'm just trying to understand. So you're not doing any hardware output experiment. You're just sending packets to the network card.
Yeah. So we are running netperf benchmark, which is simple simple sending UDP packets.
But I mean, UDP is hardware output, right? I mean, so just sending UDP, you get 1/32 of.
Yeah, for a smaller packet. So if you're sending
so on a 10 gigabit link, you get how much?
Around I mean, it's divided by 32, whatever. I mean, yeah, but for larger packet, you achieve around 3 Gbps of throughput.
On a single core?
Yeah, on single core or multiple core. I mean, only if one process is sending a packet, then it doesn't matter how many cores. So Netmap did a bunch of optimizations. One of those optimizations is this user ring, which is shared with the kernel in user producer-consumer manner. So they filled this.
So actually following Ram's question, right? So all of this overhead, ranging from 32x for 60 byte packets and 4.5x for even bigger packets.
all of it is happening because of
the user and kernel interface. So when user sends the packets, kernel copies the packets into its memory and then process the packet through the wire. So they, and since this memory can be are swappable, so the pages get swapped all the time. So in order to prevent that, they have to allocate and freeing memory again and again. And so Netmap creates a large chunk of memory which is unswappable, and then share this unswappable memory with the user process. Now user can directly put packets inside that unswappable memory, and then the device driver can directly put pointers inside the hardware ring, because now there is no problem of swapping the memory. And they are sending packet in batches, so they create the user ring which is similar to the hardware ring. They fill the user ring with the packets, and then device driver puts all these packets inside the hardware ring, and
all this is sort of dependent on the OS, right? So what OS is it, right? Based on this OS.
So this is the Netmap work. It is evaluated on Linux. So they
Look at the Windows implementation.
Netmap.
Server side Windows OS is supposed to support high bandwidth network.
Yeah, but this work is evaluated on Linux. This Netmap work. This is not my work, so I am. Let's consider a scenario where instead of running these applications, we want to run an entire operating system on our system. So notice now we can't allow the guest operating. We call this operating system as guest operating system, and our hosting system is called host operating system. So we can't allow guest operating system device driver to directly access your devices. So what we do that when the guest operating system tries to send the packets, we take a trap inside the host OS, and then host OS emulates the behavior of the device in such a way that the guest OS feels that it is talking to the real device. Since the software stack plays a critical role in overall throughput, this trap and emulate behavior leads to severe performance penalties. The reason why we need to do this trap and emulate, because we want to run untrusted guest OS. If the modifications are allowed, we can do much better. So for example, instead of taking this trap, we can create another process which is running on some other core, and we can create a shared queue between our guest driver and this process. So when the guest needs to send some packets, it puts those packets inside the shared queue and do some other work. Meanwhile, the other process which is running on some other core will process these packets, and once the processing is done, it notifies the guest driver. So even if we run this network framework inside our Paravirtual guest, we found that it performs very bad, and since it requires an extra core for side core emulation on uniprocessor setting, it performs very bad. So here is another work which further optimizes this Paravirtual interface by doing the similar kind of optimizations that the Netmap does. So it profiles the guest and host network stack, and then did some optimization like memory pre-allocation, batching, and eliminating copies, and they achieve very good performance. So the reason why we need to do this Paravirtual, why we need to use Paravirtual driver, trap, or emulate, because there is only one hardware ring and it has to share among all the guest OS and the host OS. So hardware vendor comes with this special devices which has multiple queues. Now you can assign one queue each to each guest OS, and now the guest can directly write to those devices, and since there is no sharing between these queues, there is no security issues. So we can achieve bare metal performance, line rate performance using SR-IOV devices. But these devices come with some drawbacks because they have limited number of queues. So now you can support only as many gates as the number of queues inside those devices. these devices are hard to migrate. They need extra device, they need extra hardware support, and even with the small number of guests, if these guests tries to communicate with each other, they are limited by the hardware device bandwidth. And I will show next that this problem occurs in network function virtualization. So hardware middle boxes are very common these days. So widely used hardware middle boxes are firewalls, proxies, etc. But there are drawbacks of these hardware middle boxes because they are inflexible. And so if you want to add some feature to the hardware middle box, it is very hard. They are power hungry. They are expensive in terms of money, and they are difficult to manage. Often it requires a specialized person to manage these boxes. So current trend is towards network function virtualization, where we run these devices as a software inside a virtual machine running on commodity hardware. And so often some packets needs to be processed by several middle boxes. So often these middle boxes needs to communicate with each other. So if you use SR-IOV devices and one middle box needs to communicate with other middle box, it is limited by the device bandwidth. And in the worst scenario, sometimes when a guest sends a packet to another guest, it goes through the external switch and then go back to the guest. So another work which NetVM, which found that if they use 10 Gbps SR-IOV device, they found only 5 Gbps of throughput when they use L3 router as a middle box. Yeah. Another possible scenario is you can create a virtual switch. So now you don't need to send, if the guest needs to send packets to each other, they can send through a virtual switch. They don't have to send through the external device. But now the host has to intervene in every communication between these middle boxes. So this is very slow. In our using our system, you can run this virtual switch directly inside the guest. So now you can run software switches inside the guest, and the guests can communicate with each other directly without any host intervention. Another example is firewall. So firewall are centralized systems. So the only place you can put this firewall is outside your hosting system, because all the packets needs to be processed through this firewall. But in our technique, you can run these firewalls inside the guest OS itself. So you don't need extra device for that. So this is our.
Are you saying you'll run the virtual switch in the guest?
Yeah.
And that's your thing?
Yeah. So we in our technique we directly expose the network card directly to the guest in safe and secure manner. So by secure I mean that even if the guest OS can directly access the network device, which is also shared with the host, it can not do any damage, and we don't require any SR-IOV support, SR-IOV device or hardware support, and we also allow in-guest switching, and we are also secure against malicious guests. So this is some results from this work. So we found line rate performance even with 60 byte packets.
I want to ask a quick favor to you, slide. So you don't need a special SR-IOV device, which means that there is no different queues for each guest. The hardware doesn't provide any such thing.
Yeah.
So each guest will access the hardware directly as though it owns it directly.
Yeah. Yeah.
So tell me intuitively, why would one guest not be able to overwrite what another guest has done?
Yeah.
How would isolation be provided?
So in our case, the host insert a Paravirtual driver inside the guest, and it can ensure that the guest cannot interfere with the operation of that driver. So
I see, but the driver is trusted.
Yeah, driver is inserted by the host. Now that driver is trusted, and the host can ensure that this is run in some sandbox. So it is sandboxed from rest of the guest OS.
I see. So it's like the driver is the agent of the host that is running inside the guest.
Yeah.
and somehow the guest should not be corrupted.
Yeah. So we achieve around line. We achieve line rate performance even with the 60 byte of packets, which is 33% improvement over ClickOS for send and 116% for receive. Our technique is paravirtual, so we require guest side drivers, which we call Fastio driver, and we establish a trust between driver and the host OS. So, so in our technique, the host OS insert a trusted device driver, which we call Fastio driver, in the guest address space, and once this driver is get loaded, it marks all the code pages of the driver as read only, such that the guest OS cannot change the code of the driver, and then it computes the cryptography hash from the guest driver code pages to verify the integrity of the driver. We don't trust the guest OS in any manner, and we assume that the guest OS can change any memory location and can execute any arbitrary code. Okay, so the way
I don't know what third and fourth bullet seem kind of contradictory, right? If you are trusting the guest OS, why are you doing
guest
integrity verification of guest OS?
No, the host insert a trusted driver inside the guest address space, and it trusts its own driver, but it don't trust the other part of the guest.
So when you say guest code pages, you're referring to just the driver.
Yeah, driver code page.
Driver,
Yeah,
not the guest driver.
yeah. So the way your driver access the network device is a memory map device. So some part of the physical address space is treated as the device memory, and if you map those pages inside your page table, you can directly talk to the device. So we map the device pages in the extended page table of the guest, as then now guest can directly talk to the device by adding those pages inside its page table. So we create a privileged page table where we map all the device pages, and our Fastio driver has only one entry and exit point. During the entry we load the privileged page table, and during the exit we load the previous page table, such that now the privileged page table is only operational only the time when the Fastio driver is running. And but the malicious guest can add device pages into its own page table, or it can create a new page table, add as the device pages into it, and load this page table. So we configure our hardware to take trap on all the instructions that can potentially change the guest virtual address space, that are move to CR3, move to CR4, and move to CR0. Move to CR3 is used to load a new page table, and move to CR4 and move to CR0. Using that, you can change paging mode, disable paging, etc. And to protect against guests to add device pages inside the page table, we protect the guest page table. So when the guest tries to write anything into its page table, there is a trap in the host, and then host can emulate those changes. But notice I said that we need to load this privileged page table inside our Fastio driver. So at the beginning we need to load the this privileged page table, and during the exit we need to load the original page table. There will be two traps inside our Fastio driver if we configure our hardware to take trap on move to CR3 instruction. So we need to do something else in order to save those traps. So this is our technique, which we call this is a new technique proposed by us, which is dynamic binary opcode subtraction. So notice a guest OS can execute any instruction if that instruction exists in the address space of the guest OS. So if you can remove all the opcodes corresponding to move to CR3 instruction from the guest address space, guest cannot execute those instructions. So we use extended page table to mark all the guest pages as non-executable at the beginning, so the guest cannot execute any instruction in the beginning. And when the guest tries to execute any instruction, there will be a trap inside the host. Then host can scan the page which the guest is trying to execute, and if it finds move to CR3 opcode on that page, then it replaces that opcode with int3 instruction. Int3 is a special instruction which is used by by software debuggers to put breakpoint. We configure our guest OS to take trap on int3 instruction. So there is a problem that this move to CR3 opcode could be a part of middle of an instruction. For example, if you see the first move instruction, it contains move to CR3 opcode, and if we replace it by int3 instruction, now the instruction gets changed. So there will be no trap inside the host. Instead, the guest behavior will be changed. So to deal with this problem, we identify the correct instruction boundary and pass the instruction from the beginning. So let's see how it's works. So for example, this is the guest code page, and initially the guest in trying to execute this instruction at PC4. So there will be a fault inside the host. Now the host keep this information with every page that what is the instruction boundary it knows on that page, because the guest host doesn't know what are the actual guest boundaries. So it adds it keeps this metadata. So it updates this known instruction boundary at PC4. And now it scans the page and it finds that at PC3 there is this move to CR3 opcode, but it doesn't know the correct instruction boundary. So it executes this page in trap and emulate manner. Let's say after some time it found a fault on PC1. Now it knows a valid instruction boundary before PC3. So it disassembled from PC1 and it found that the PC2 at PC2 there is an instruction which contains this move to the CR3 opcode. So now it can pass the whole instruction with int3 instruction, and now it can retain the execute permission on that page. So now the guest one can directly execute that page. So we run a SPACint benchmark and a fork-weight benchmark to evaluate the overheads of our DBOS technique. So fork-weight is a benchmark which creates around 40,000 processes in a loop. So since there are too many processes, there is a lot of paging activities and a lot of scheduling activities. Hence we found around 18x overhead of DBOS in case of fork-weight. But for middle boxes, only one process is running inside the guest OS, and there shouldn't be too much demand paging and scheduling. So there is no overhead of DBOS when we use for our network applications. So this is our Fastio pseudocode corresponding to our Fastio driver. So there is only one entry and exit point to the Fastio driver, and you can see at line 5 we are loading the privilege page table, and at 13 we are loading the old page table. So notice this instruction which loads the privilege page table is move EX to CR3. So it moves the contents in the EX register inside the CR3. So now a malicious guest can just load any arbitrary page table inside the EX register and can directly jump to this instruction, and it can access the device pages. Fortunately, there is a support, is a hardware support which allows host OS to configure guest OS to take trap on every CR3 instruction, except it can maintain a cache of 4 values on which it wouldn't take any trap if you execute move to CR3 instruction. So we add our privilege page table in value inside that cache, and the other 3 values can be used for the applications which is calling this Fastio driver.
So will that limit actually the number of applications the guest can run?
Yeah, number of applications that can use. Not limit. I mean, so if you use more than 3 applications, there will be trap, because if all the applications would have different page tables. So for 3 applications we have a space in the cache, but more than 3 applications inside a virtual machine. But if you see the current virtualization trend, the trend is towards lightweight virtual machines where we run only one application inside the guest OS. So in that scenario, all the demand paging and scheduling is the part of the host OS. So in that case, there wouldn't be any overhead.
Does this also require or allow that the network stack logic also be moved into user space, or that is handled by the guest OS? Like
yeah, that is the original. So we are running the Netmap thing inside the guest OS. So whatever the Netmap stack, it is inside the guest OS. Now guest OS doesn't need to take any track. So on the transmit path, we plus our own Netmap ring, any application plus own Netmap ring to hardware ring, and on receive path, it reads the hardware ring and enqueues the packets to the respective guest to provide mutual exclusion among these guest OS Fastio drivers. We use a shared lock through privilege page table, and we also do zero copy on both transmit and receive side. So receive side zero copy has a potential for mismatches, so we need to copy packets when there is a mismatch. Also the receive side zero copy has a potential for man in the middle attack, so we show our results with and without receive side zero copy. So we found no overhead when we found line rate performance when we are running only one guest VM, but with 4 guest OS on 60 byte packets received, we found a throughput degradation of around 37%. We also implement in-guest software switch. So now suppose 2 guests needs to communicate to each other, it don't really have to do through the network device, so we can do it in software. So here we don't have to we are not limited by the device bandwidth, and we found very good throughput with this several combination of sender and receivers. So to conclude, we use dynamic binary opcode subtraction for improving IO virtualization performance. We achieve near bare metal performance, which is up to 2x faster than best known paravirtual solution, and we also do in-guest switching. Any questions?
has anything been merged into Linux kernel yet?
This is still a work in progress, so yeah.
Can you comment on the practicality of a paravirtualization solution like this, and how do you actually deploy this? Because you're creating a driver that is now tied to Linux or something.
Yeah, so paravirtual driver or so anyway, in the current scenario also there are different drivers for the Windows and Linux and all the operating systems, right? Not all, even if in the guest OS is Windows, right? Some guest OS are Windows, some guest OS are Linux. So there are different drivers inside those things. Yeah. So yeah, in order we make in order to support different guest OS, we need to make them compatible with each other. So I think we only need to change the interface. I mean, so so somebody is calling that guest driver, right? So if we just use the same calling convention in different guest OS, I think we can support. But anyway, you need to write. You need to understand what is the existing interface between the driver and the rest of the OS, and you need to write a driver in such a way.
So, VMware has some virtual switch
Yeah.
solutions right now, right?
Yeah.
So, would it be correct to say that you could support the same interface that they support, or
Yeah,
any additional?
I think we can support all the functionality that the VMware virtual switch supports, but their virtual switches work inside the host. We can do a bit higher.
Say that any virtual appliance, anything that has been written for the switch,
Yeah.
and with either no modification or very little modification use your driver.
Yeah. So I still need to investigate that what kind of functionality that the vSwitch supports, but I am sure that whatever you can do inside the host, you can also do inside the host, right? whatever the host driver can do, the guest driver can do the same thing.
I have one question, which is what all attacks do you prevent? Is it like bulletproof, or can I do something? You showed me a bunch of techniques like DBOS and so on. If I'm clever, can I circumvent all of those kinds of things and compromise your driver anyway?
Yeah, so we are not able to think about any such kind of attacks, but yeah, but we don't have any formal proof that our thing is correct.
So the hardware has other features, right? The hardware name.
Yeah.
Can your system work with that? Let's say, if you have separate queues or if you have offload, the other functionality, how would you run that in multiple layers?
I think we can so even if this hardware has multiple queues, they have limited number of queues, right? So there are fixed number of queues. So we can make the queues more scalable. So one queue could be shared among multiple guests. That we can also support. So in that way we can improve the scalability of the existing hardware support.
But there may be functionality in the hardware which cannot be parallelized, like let's say doing some encryption in the hardware.
Yeah, so it's within the hardware, right? So we are putting the device driver inside.
With multiple guests.
These paravirtualized drivers risk control, so that can make sure that is that right? I mean, your driver is basically the one that's going to talk to the hardware.
Yeah. Only the driver which we are putting inside.
Right, but the multiple guests.
So we can ensure the mutual exclusion, right? Yeah.
That will create a lot of overhead, right? I mean, the whole point of hardware offload is.
Yeah. So we are using a shared.
All the guests have to basically do mutual exclusion.
Even if this, when you are talking to the device, right? So you do some MIO. The MIO is going anyway going to be very slow. So when you talk to the device, it is really slow. So even if on your system, if your device driver when your device driver talking to your device, it does in some mutual exclusion. So even if you have a lot of cores, so only one core is directly talking to the device at one time. And this SR-IOV device has multiple queues, so they can do in parallel. So on different queues, different drivers can talk to the different queues. Yeah, but if you want to share one queue among the different guest OS, you have to do in some mutual exclusion.
But let's say since you have 4 queues and 4 guests, can your system parallelize them?
So they are already parallelized. I mean, 4 queues and.
No, but each guest will have access to only one queue.
Yeah.
That's what you do.
No, in our case there is only one queue. There are no 4 queues. There is no special device, so there is only one queue, and all the guests are sharing the same queue.
No, but yeah, if you're not using SR-IO device, right? If you have an SR-IO device with say 8 queues or whatever,
Yeah.
and you have 4 guests, how will you you have to manually divide it up, or you know what I'm saying?
If there are 8 queues in SR-IOV devices and there are
4 guests.
then they can just use one queue each, right?
So maybe they want to use 2 queues.
So
No, so that's like a.
yeah, so one queue could be shared among the one SR-IOV queue could be shared among the multiple guests, but you need to do it in some mutual exclusion. Thanks.